All right, so we're going to continue with the functions today. We're going to introduce another term. We'll talk about polynomial functions. And after that, we're going to cover a lot more the domain and range, especially from graphs, and also of various functions. So polynomial function is basically a function like this. That's equal to some polynomial here. Okay, the expression here. So this is a function notation we talked about the other day. So the f is the name of the function. Okay, and x is the variable. And here we have some expression. And today we're going to see that this expression is a polynomial. We saw what a polynomial is. A polynomial is basically an algebraic expression. That's what we saw the other day. It's an algebraic expression where we don't have negative exponents. You don't have, for example, x in the denominator. Also, you don't have radicals over the variable. So that's what a polynomial is. A polynomial is an algebraic expression without these forms here, or without these terms. So again, when we talked about polynomial the other day, we spoke in detail. We said a polynomial does not have a negative power, does not have x in the denominator, or something like this, a radical or a power that's, for example, a fraction or a decimal. Okay, so functions made with polynomial, that's what we're going to talk about first, and later we're going to talk about the domain and range a little more in detail that we talked about last time, especially with graphs. So as an example of the functions we saw the other day, we saw linear functions. That's when we had, for example, something like this, ax plus b, where the power of the x is 1. Okay, that's why we call this a linear function, because when you graph it, it's a straight line. Then we saw another type of functions. We saw where the power here was 2. So technically something like this, ax to the second plus bx plus c. Okay, so the highest power was 2. That's why we call this quadratic. Okay, quadratic function. And the graph of this, as we saw last time, was a parabola. Parabola facing up or down, depending on the sign of this number. If this number is negative, this parabola faces downwards. If it's positive, it faces upwards like this. I believe we introduced also a function like this with third degree. So third degree, something like this, but the highest power is 3. And we talked about it, we said the graph was a hyperbola. Actually, not this one, but the graph of a third degree function looks like this. Hyperbola is when you have x in the denominator. Hyperbola, for example, 1 over x. The graph of this function looks like this. Okay, hyperbola. This is a parabola, but this is a hyperbola. And this is a parabola. These are the type of the functions that we saw so far. So today we're going to see polynomial functions. That means only functions like this without negative powers, without x in the denominator, without a radical or something like this. That's what we call polynomial functions. They're all generally in this form. Of the power could be anything. The power could be any number, 1, 2, 3, or more. So in general, we write the standard form of polynomial functions like this. There's always some a number here. And that number is followed by, what is that? That number This an, whatever that might be. This is the coefficient as we talked about before. This is the power. So this power could be anything, like here could be 1, linear, could be 2, could be cubic, a function, well, in this case the graph looks like this. And usually we write these in descending order. So if there is a power here, the next one should be lower than this power. So I could say there's another term here. So for example, an minus 1, and the power should be smaller than this by 1. And it keeps going like this. So it goes in a descending order of power. So n minus 2, x n minus 1. Just like here, for example, you have 2, you have 1, and so on. For this one, you could have ax plus x to the third, plus maybe bx to the second. As you can see, the power goes down, plus maybe cx, plus maybe some number d. So the power is 1. Okay, you could have any number of terms. These are what we call terms. This is a coefficient, this is a variable, and this is the exponent, or the power of the variable. So a function could have one term, for example, just f of x equals 2x, or it could be 2x plus 5, could be this, so it could be any number of terms, as long as the variable doesn't have a negative power, the variable is not in the denominator, doesn't have a radical or a fraction or a decimal as a power. So if you keep going like this, will end up with something like so n minus actually minus 2 here. So n is minus 1, n minus 2, minus 3, minus 4, all the way to 1. Okay, just like we saw here. It was 3, then 2, then 1. So if you have 10, for example, here, then next one is 9, then 8, and so on, all the way to 1. And the final term, for example, here, this one doesn't have a variable, it's just a constant term. So we can call this one, for example, A0. Okay, so that's the final term of the polynomial. So we can call this all the way maybe to 1. Okay, so this goes down to coefficient. This is just a notation. This is just the symbol for the coefficient, but it doesn't have to go down here. It doesn't have to be here, for example, 7, then 6, then 5. But the power does. The power decreases as we go from one term to the other. When we arrange the terms in this form, we start with the highest one. So the highest power, as we saw before with the polynomials, is the degree of the polynomial. The highest power of all the variables is the degree of the polynomial. Also, since we're talking about polynomial functions, that's also the degree of this polynomial function. So this is just the general form or the standard form of polynomial functions. And it could be one term, like I said, it could be many, could be anything. Again, as long as the power does not have one of these, does not have one of these cases here. And it could be any number of terms. So the last term here doesn't have x, but you can think of it as x to the power 0. What is x to the power 0, everybody? What's
Just 1.
0?
1.
Is 1. Okay, is 1. That's why we don't write that x0, because x to the power 0 is 1. So this goes down all the way from n, keeps decrementing or decreasing by 1 all the way to 0, which we don't have to write usually. X to the power 0 is just 1, so a0, or the constant, for example, here. Let's try an example here. Write an example, maybe, so f of x, 2x to the 7th. Okay, so this one doesn't have to necessarily increase or decrease. Could be any number here, any factor or coefficient. Maybe 6x. Actually, we use a different number, 6x to the 6. And then it decreases. It doesn't have to decrease necessarily by 1. Okay, as long as the next term is lower. It could be, for example, 4x to the third. Always arrange the term from the highest to the lowest in terms of power. Then maybe negative 2x 2, finally 5x. So 5x means 5x1. We don't see a power of a variable, that variable, and that power by default is 1. And finally, some constant, maybe 8. 8 for the last one by itself, the constant here. You can say 8, or you can also say 8 times x to the power 0. Right? It's the same thing. We don't usually write this x to the power 0, so you can write it like this. Okay, so that's the notation of polynomial functions in general. But usually we will deal with functions or polynomial with maybe 3 or 4 terms max. Okay, you won't see something very long like this. You take like just a few terms, 3 to 4. Usually the powers hover around, let's say 3 or 4, fourth power. Okay, so this is just the standard form of the polynomial functions. Don't let this notation scare you. It just means general or standard form of polynomial functions. Okay, so now we're going to see how to deal with polynomial functions. It's very similar to polynomials themselves. So when we worked with polynomials before, remember we added, we subtracted them, we multiplied them. We're going to learn how to divide them maybe in a class, the next class or the following class, when we do factoring. That's when we divide polynomials. But the way we deal with them is very similar to polynomials. So let's see how to add. So let's call this one maybe definition. As always, we define the topic or the keyword, and then we work with that with examples. So let's see how to add and subtract polynomial functions. Again, they're just functions. So this is just a fancy name because they're made of polynomials only. So relatively, they're easier than other types of functions. For example, this is not a polynomial function because it has x in the denominator. This one is a special one. We're going to talk about it later, and we'll discuss why the graph looks like this when we talk about the domain and range of functions. So addition, subtraction of polynomial functions. So to add or subtract 2 functions or 2 polynomial functions, we need at least 2, just like we did with polynomials. Basically, think of them as polynomials with names or with notations like this. So let's say 2x plus 5. We need another one, and maybe negative 5x plus 3. So when you have 2 functions like this, so basically you can ignore this. Think of it as this is a polynomial, this is a polynomial, specifically a binomial. You can make it a little different like this. Okay, so this is a binomial because it has 2 terms. What we call a polynomial with 3 terms? Everybody, what we call a polynomial with 3 terms? This is a binomial. What would this one be?
I don't actually remember.
Wait, it was minor. No.
It has 3 terms.
Yeah.
Monomial is 1. Binomial is 2. What about 3 terms? We call that trinomial. Okay, trinomial. And then anything above that, we call it a poly. Poly stands for many. Poly for many. So we could add these very similarly to add in polynomials, because these are again just polynomials with these notations next to it. So if the question says find f of x plus g of x, all that means is you write f of x. So f of x equals to this expression, and addition and g of x. G of x, which happens to be this, so I'm going to write all those terms. So we get a 5x to the second plus 3x minus 1. In case of subtraction, you have to include the parentheses here, like this. But if you have addition, no need to put the parentheses. Just combine the similar terms. Okay, if this was a minus, you would distribute first. We're going to see that when we subtract. For now, it's an addition, so we just combine like terms. So we're going to combine these two. 2x plus 3x. Again, combine the coefficients with the signs. It's a positive 2. We have a positive 3, so that's positive 5x. And we combine 5 and minus 1. So positive 5 minus 1 would be 4. And then we have this term by itself, negative 5x to the second. It doesn't have a like term to combine it with. So we just bring it down. So we added the two polynomials, the binomial, trinomial. We ended up with a trinomial. How do we rearrange this so it looks in the standard form of polynomial functions? How do you rewrite this? We want it to look in this form. So which term do we write first? Which term from this do we write first?
Wait, let me check.
Okay, how do we write, or how do we arrange the terms of a polynomial again? See the powers here?
We have to multiply.
No, we're not multiplying, we're done combining. We just want to rewrite this expression, the same one, in this form. So which term goes first?
5x on the second power?
Right, negative 5x to the second power.
Oh,
So,
negative 5x, sorry. Yeah.
right, so the polynomial functions always arrange the powers in a descending order from the highest to the lowest as you go down. So negative 5x to the second. When you move
Plus 5x.
right. So whenever you move a term, make sure you move the sign with it. The sign of this coefficient is negative 5. So we move this to the front using the commutative property. So we're going to move this over. This moves back. It's a positive 5x. There's an invisible positive. So write 5x. And positive 4. So it's better to write it this way. So we have power 2. We have power 1. You can think of this as power 0 if you want. You don't have to write this x0, but you can see it nicely here in this form. So the power goes down. The coefficient doesn't necessarily have to go down, but there's always going to be a number there for a coefficient. So 2, 1, 0 is the sum of the two. Again, no need to write this x0, but it looks nicer like this, like the standard form when you write it. Okay, that's the addition. Again, very similar to polynomials and algebraic expressions that we discussed before. So this is, second part is subtraction. So with this, if it's written like this, the question says find this, so you don't have to figure out the order. So order is the same, you keep the same order. But if it's written in a word problem and it says subtract this from this, or find the difference, so you have to figure out which one goes first, as we did with polynomials. If it says subtract f from g, which one do you write first when you subtract? The question is subtract f from g. How do you set up the subtraction? Which one do you write first? Everyone? Talking to everybody, please engage. If we had to subtract two polynomials or two numbers, for example, 2 and 7, how do you set the subtraction? How do you set it up?
7 subtract 2.
Right, the from goes first, okay?
From G, from F.
That's right. So if it's in a word like this, you have to figure out which one goes first. But if it says find the difference, please mute your mic if you have background noise. But if it says find difference, it says find difference of G and F. Which one goes first when you subtract? Find difference of G and F. So we keep the same order. If it says find difference, G minus F. Okay, but if it says subtract F from G, remember the from goes first. Always the from goes first, then the first one. When you write the first one, make sure you write it in parentheses when it's a polynomial. what a function, polynomial function, you write it in parentheses. Okay, that's if it's in a word problem. But in this case, if it's written like this, so you don't have to figure out the order. You keep the same order. It's already set up for you. So this will be f of x, whatever f of x is. Again, it's 2x plus 5. This minus, okay, because we're subtracting. And you have to use the parentheses with subtraction. It's very important because that will change the signs of g. So this is g, so f minus g. We wrote f minus and g. So g has to be in parentheses, so it's negative 5x to the second plus 3x. And we write that bigger. Minus 1. Okay, this is g. We write it in parentheses. Since we're subtracting, all these signs will change because when we multiply these by this negative, which basically is a -1, all these signs will change. With addition, no need to change any signs, no need for parentheses either, just combine like terms right away. So think of this again as a -1, then we distribute. So -1, negative times negative will be positive, 5x to the second. Negative times positive is a negative. Basically, we flip in each sign inside because of this negative. So 3x, finally, the negative turns into a positive. Or you can say negative times a negative. Now we can combine like terms. So we can combine these two. So it's 2x minus 3. Positive 2. What is positive 2 minus 3?
Negative
1.
Negative 1. That's right. And then we have 5 and 1. Positive 5, positive 1, positive 6. We have this term by itself again. There's no like term with the second power to combine it with, so it will be 5x to the second. Again, rearrange your terms from highest to lowest. So we're going to write the positive 5x first to the second, followed by negative x. When you have 1x, you can just say negative x. You don't have to put the 1 here. You don't have to, so we think of it like this. So we have an invisible 1, invisible 1, or you don't have to write those. You can just say negative x, followed by the constant 6, which you can consider. Think of it as 6 to the power 0, because this is 1. 6 times 1 is 6. But again, you don't have to write this. You don't have to write the 1 here.
Professor, why you didn't take the 6 before the -1? I think you said you was going to be taking biggest number to the smallest number.
Why did I not write the 6 before the -1?
Yes.
So when we arrange them, we look at the power. So the power here is 1. This is what we arrange. Power.
Okay, I forgot you said the invisible 1. Okay, I understand now. Okay.
But, okay, so this is basically the final answer. So the standard form here. So this is what we arranged. Not 7, 6, 3. We don't care about 2 or -3 or 4. Coefficients don't matter. The powers do. So this is trinomial with degree 2. So the difference with the subtraction of the two functions is this. Now let's see how to, number 3, maybe multiply. Again, very similar to multiplying polynomials. We just added this notation next to a polynomial to give it a name or a function. Let's multiply the same one. So f times f of x times g. It's usually written like this. Or it could also be like this, f of x times f of g. So do not confuse this multiplication with composite function, composition of functions. So last time we saw that this little circle means f composite g of x. F composite g of x. That's when we plug g into f. This is not a multiplication, but this is a multiplication. When you say f of g, just basically going to take f and multiply by g. So do not confuse multiplication with composition. So they're not the same thing. So it could be written either like this, or it's also the same as f, actually g here, f times g. Either one is fine. Same thing with the addition or subtraction. This is the same as saying f plus g of x. Okay, we can write them separately, or we can write them together and of x. So this means of x. It does not mean multiply. It just means they both have x as a variable. They both have that same variable. So let's see how to multiply this. Very simple. So just write the function, the first function f times it by g. The first function is here, 2x plus 5. Multiply, no need to for that, we're just going to use parentheses. Multiply by g of x, which happens to be this, negative 5x to the second, plus 3x minus 1. Then we distribute this. So we have 2 terms times 3. How many multiplications are we going to have if you multiply 2 terms by 3 terms? 2 by 3, how many multiplications? If we distribute this, it will be 2 by 3 will be 6. 6 multiplications. So let's see those. So 2x times negative x to the second will be negative x to the third. Okay, so times negative 5. We have x1 here. When we multiply by x2, we add the powers. Okay, that's what we saw when we did the rules of exponent. Then this one, 2x. What is 2x times 3x? What is it? 6. 6 what, everyone? Everybody in the room. That's right. We add the powers. So x1 times x1 is x2. Okay, and then third one is negative 1. So 2x times negative 1 is negative 2x. Okay, so basically we did this 3 times. Now we're going to do the same thing with this one. So we're going to times it by these 3. So positive 5 times negative 5 would be negative 25x to the second. Then you have positive 5 times positive 3x, that's positive 15x. Finally, positive 1, positive 5 times negative 1 is negative 5. We distribute all of them, so you have 1, 2, 3, 4, 5, 6. So we have 6 multiplications, as we said, because it's 2 terms, binomial by trinomial, total of 6 multiplications. Then we're going to try to combine any like terms, simplify them. So the highest term here is x3. There's no other term with x3, so I'm just going to bring it down. Okay, and cross this out. Then we have 6x to the second. We're going to combine this with this one. So positive 6 minus 25 is negative 19x to the second. And also combine these two. They both have x1 and x1. So negative 2 plus 15 is positive 13x. Finally, we have this constant by itself. There's no other constant, so write it like this. You can see the highest power is 3, then 2, then 1, then power 0 here. And that's basically, again, polynomial function in this form, standard form. Again, no need to write the x like this. No need to write the x1 here. And that's basically it. So it's very similar to multiplying polynomials. Now let's see how to evaluate number 3. See how to evaluate polynomial functions. Okay, any questions, everybody, so far? Everybody know this? Okay, so basically all we're doing again is adding. We're just adding and subtracting. just like we did with polynomial. Evaluating functions. So let's take a couple of functions, maybe f of x. Is x to the second, probably g of x, 3x minus 1. Let's find f plus g of 1, for example. So you see here, we don't have x. If you have x, like here, you just add the two, okay, just like we did here. But if you have a specific value, what this means is basically evaluating these two functions. So we're doing f of 1 plus f of g. Or g of 1, actually. G of 1. Okay, so when you have f plus g or f minus g or times g, whatever it is, you have a specific value. That's when we need to evaluate. The result will be a number. It will not be a function like this, but it will be a specific value because we're evaluating it based on a specific value of x. So x here is 1. So we're going to find f of 1. So to find f of 1, we're just going to plug 1 into f. I'm going to plug 1 here, 1. So f of 1 will be 1 to the second plus g of 1. G is this. We're going to plug 1. Okay, this is g. It's 3x minus 1. So we're going to find g of 1 is we're going to plug 1 here and here. Will be 3 times x, which happens to be 1, minus this one that comes with the function. And then you simplify your expression. That's 1 plus 3 minus 1. Cancel the 1s. You get 3. Okay, as you can see, it's a specific value. When you have a value here, expect to have a specific value, not a function. If you have x here, that's a generic. That means you need to multiply or add the two functions. And then, for example, you end up with something like this, not a specific value, because this is a generic. We have x here, not a value. And the same way works for addition and subtraction, exact same way. If this was a minus, here, it works the same way. You're just going to have a minus here instead of a plus. Let's look at the multiplication. Let's say you have f of g. Okay, f of g of maybe 2. But actually, let me make it negative 2. Again, don't confuse this with the circle. That little circle means f of g or f composite g. That's when you plug g into f. Okay, but in this case, we have a dot, or if you don't see anything at all, there's nothing at all between f and g, it's still a multiplication. But again, do not confuse multiplication with composition. It's a common mistake that people make. Okay, so we have f times g of negative 2. So how do you find this based on the same concept here? Could someone tell us what to do here? Everybody?
So we're gonna find the 4 minus 2.
Okay.
So it is going to be minus 6
Before that,
minus 1. Oh, wait, why are we finding? First we have to find the g minus 2.
again, that's for if you have this.
Oh, is it? I thought. Oh, I thought it was composition. My bad.
All right. So let me say that again. So if you have this little circle here, that means composition. It's not a multiplication. So that's when you find this first. You find g of negative 2. Then you get some value, whatever, for example, a. Then you take that a and you plug it into the first one. So you find this, whatever it might be, you plug it into the f. So into the f of whatever you get from here, the a goes here. Then you find your answer. Well, this one is different. This is a multiplication. So you're just going to find f of g, f of negative 2, and times it by g of negative 2. So basically, f of negative 2 times g of negative 2 times. Okay, it's quite different. They're not the same. So these two are not the same. If you do the value, if you do the math, the value will be different. Okay, so let's find f of negative 2 first. If you plug negative 2 here, what do you get? F of negative 2 will be, what is f of negative 2?
So is it 4? Isn't going to be 4?
Right, before it would be negative 2 to the second times. Then we need to find g of negative 2. So we're going to plug negative 2 into g. So this is g. We're going to replace negative 2, x with negative 2. So it'll be 3 times negative 2 minus 1. We need some brackets here. You have a multiplication. This times whatever this is. So again, negative 2 times negative 2 is 4. Multiply. We're going to use the order of operations. So we're going to work inside the parentheses. So negative 3. This is negative 3. Negative 3 times 3 would be negative 9. Finally, this is negative 36. Okay, so that's how you evaluate functions. It could be two functions here, could be more, could be f times g times k times h, works the exact same way. Just evaluate each one individually, and then either add them, multiply, depending on the question. Again, do not confuse this with this here, with the composition functions. Okay, everyone, does that make sense? Any questions? Everybody in the room, I want to hear from all of you. Are you guys okay? Any
Yes. Yes. Yes, Professor.
No question, Professor.
Right, so please feel free to ask everybody here. If you have any questions, please feel free to intervene.
Oh yeah, I do have a question, Professor.
Yep.
About we're gonna have a meeting, right?
Yeah, we'll talk about that after class, okay?
Oh, okay.
I'm asking now if you have any questions regarding this. Everybody, if you have any questions, feel free to ask. We're going to talk about the exam and everything at the end of the class. Okay, so that's evaluating functions. Very simple, just adding and subtracting, basically polynomials. The other thing that I wanted to talk about today is domain and range of functions, various functions, including something like this. This was part of maybe the previous unit 3.5, 3.6. Let's just say domain and range. Some of it is not in the book. Domain and range of functions. So we saw before there's a few ways to write functions or the results of functions. So we saw the most first one we saw was a table. When you have x, you can have a column like this, x and y. Let's say 2, -1, and 4. Maybe 5, 8, and 6. So this is a domain, this is a range. So we learned how to write this in set notation. So the domain is D, is basically the values of x. This is a domain, and then you say, you write colon, open curly braces, and you write all these elements of the first value of each pair, usually in a ascending order from the lowest to the highest. The lowest here is -1, then 2, and 4. And what is the range of this function? Range is the values of y, which are these. So
5, 8, 6.
That's right, 5, 6, 8. You also arrange them from the lowest to the highest. We also saw how to find the domain and range from graph. So, for example, you have this graph like this, and we can find, let's say, something like this. We can find, this is the x-axis, this is the y-axis. Let's take this notation here. So this is probably about -3. Let's make this maybe 4. about -1 here. Let's make this 2. You can also get the domain and range from a graph. So if you look at this graph, the values of x go between what values? The values of x. So this graph, this is the graph. So the domain or the values of x, they go from where to where? This graph here. The values of x, they go between what values from the graph?
It's 4 minus 1. Wait, yeah, 4 minus 1.
No, so the x here, so the highest x possible.
Oh, that's a minus, yeah.
The highest x is here. What's the lowest x on the graph? So it goes from 4 all the way
-3.
-3, right? So all the x's are basically here. There's nothing beyond this, because the graph stops here. We have a little circle here. We have a little shaded circle. All the x's of this graph, this one, which is a function. How do you know that this is a function? How do you figure out or determine whether a graph represents a function or not? You do what the test. What do we call that test again? Everybody in the room, I feel like I'm only talking to a couple of people. Everybody else is sleeping or not in front of their computers or something. What is this a function or not? And how do you determine that?
It's a function.
Okay.
Because you said that if the two dots is connected on the same spot, it's not a function. Well, when it's not, it's a function.
Mm-hmm. So we do what we call the vertical line test. You say vertical line, it only meets the graph once. So here, anywhere you draw that vertical line test, it only meets this graph once. So it is a function. However, if you have a graph like this, if you do the vertical line test, how many times does it meet? Twice.
So
That's right. If this was the graph, it's twice. This is not a function. Okay, it's not a function.
that was right, Professor. That one is a function, right? The one that you asked.
So this one is a function because anywhere you draw,
Okay.
draw that vertical line test, you only meet once. Only meet this graph once. That makes it a function. Okay, so this is a function now. So the domain goes. The domain is the values of x. So they go between -3 and 4. So -3 and 4. So the domain again is the values of x only. So this is the x-axis. For this graph, all the values are in this interval. Now, we need to use something around these. So this is what we call set notation. Set notation. Set notation is basically when you use curly braces and we list all the elements inside and we close the curly braces. This is the name of the set. We use colon, these 2 points, colon, on the right. But when we have too many elements to list, so we have so many points here, and from -3 to 4, we have so many points, for example, -3, or here, for example, 0, 0.1, 0.2, 0.3, but so many points, we can't write all of them. Instead, we just use interval with the lowest and the highest values only. We can't list all of them. We have literally infinitely many, if you think about the decimals and everything. But here for this function, it has only 3 values here, 3 values, exactly 3. That's why we list them. But if we have too many to list, instead of writing all of them, which we can't write in one interval, in one set, instead we use the interval notation. We only need the range between what values, the lowest to the highest. In this case, the lowest one is -3, the highest one is 4. So here we use curly braces, but with interval notation, this is what we call interval notation. So interval notation, we need we only use either these are brackets, or parentheses. These are curly braces, okay? These are brackets, these are parentheses. So what do you think we use around -3? -3 here, if you're looking at this circle, what do we use here? Do we use a bracket or parentheses?
Parentheses?
We use parentheses, why? So that's right. So when you have a circle, this means this point is not included. So whenever you see a little circle here, that means that point is not included in the domain. All other numbers are fine, but -3 itself, this means skip that. It's like a hole in the graph. It's empty. We need to skip that point. So we use parentheses, which means not included. So this means all the values between -3 and 4, but not including -4. What about 4? Is it included or not?
Yes, it's included.
Included. So what do we use?
The cracker? How do you call it? The
Bracket. That's right.
the stacker. Thank you.
When the number is included, we use brackets or this shaded circle. If you see a hole in the graph like this, that means the graph is discontinued. Graph does not exist here. There's nothing here, just void. So this point does not belong to the domain. So if I said, give me some numbers that belong to this domain. Okay, does 1 belong to this domain, to this interval? Is 1 in this interval? Everybody, I want to hear from all of you. Is 1 included in this interval? If you look at the graph. Is it? Shouldn't be hard to figure out. Is 1 included in this interval? Look at the graph here. Do we have 1 here? Is it? Very good. Mirsada, please keep your mic muted all the time.
Okay.
Right, so it's been noisy the whole time. So.
But they're trying to be focused. Okay, I'm gonna do it.
You can focus with
I'm gonna be. I wanna answer question. Okay, I'm gonna mute it.
If you answer, then turn it off immediately. Okay, if you wanna answer, because there's always background noise there. All right, so 1 is here, right? 1 is included. What about, let's say, -2? Is it in this interval?
No.
No, it's not.
-2, why not?
No.
It is, -2 is here. -1,
But we don't,
We see
I don't understand.
any values, so this is the graph, right? This interval here, all the numbers between -3 and 4. All the numbers, not just 3 and -3 and 4, all the numbers.
Okay, I got it. Okay.
Okay,
So let's say that +2 is also in.
That's right. So positive
over there. Okay.
just because
2, 3, 1, yeah?
that's right. Just because it's right, it doesn't mean it's not there, but it is. So -3 and 4. What about, let's say, 5? Is 5 included in this interval?
No.
Outside here.
Yeah.
0.
0, yes. 0 is included.
There's in the middle. What about -8?
No.
No.
5. What about 3?
Yes.
Yes.
So interval means all the numbers between these, okay? Unlike the set notation. The set notation means only these specific values. That's why we use curly braces. Okay, so is 4 part of this interval? Is it included?
Yes.
Yes. Okay, what about -3?
Yes.
Is it included? Is it part of the interval?
Yes.
Nope, we said it has a hole here, right?
Oh, okay.
Okay, so even though you see it here, doesn't mean it's part of the interval because of the parentheses or because of this hole in the graph.
Also, any numbers that have the circle with the shadow is not included.
That's right. So even though you see it here, it's not part of the interval. That means this means skip that 3, but include it, because that's what the graph is.
Okay.
That's the difference between these two. So one of them is included, or the other one is not. So if something is included, we use the brackets. If it's not included, we use a circle like this. Okay, so that's how you find the domain from a graph. Same way, let's find the range. So if x, or if the domain is the values of x, the range is the values of what? What variable? The domain, or the range, as we said here, domain is the values of x, the range is values of y. Okay, so look at the graph again. Look at this graph. This is the y-axis. And tell me, for our graph, the y values go between what numbers? So this is graph. Think about it. What's the lowest y? The lowest y for this graph, and what's the highest y? That would be our range. So set that the x goes from here to here. So what's the y if you want to read it from the graph? It goes from what numbers?
It's -2, -1.
Right. Goes from -1 all the way to 2. Okay, so this is the lowest one possible. As you go up, this is the highest one possible. So all the y values are here in this range. So they range from -1 to 2. And what do we use around -1? This -1, is it included or not? Is not
Included.
bracket, that's right, because it's included. We have a shaded circle, that means included. What about 2?
The open circle. I mean the parentheses, sorry.
Right, the parentheses, because we have a hole here, it means do not include that. Skip this number. So you see it here. So we're going to use parentheses. Okay, so that's how you get the domain and the range from a graph. So depending on this, so if you have points like these, that means the graph stops here. If you have an arrow here, or both, that means the x and the y do not stop. They keep going, extending in both directions. For example, let's say, take this graph, and something like this. This is the x-axis, the y-axis. So this graph starts from here, from this circle. This is about, let's say, -5, maybe -2 here, and probably 4. Now, same thing. Let's try to get the domain and range of this function. It's a function because of the vertical line test. Let's start with the domain. The domain goes between what values? Think about the x of this graph. It starts from where? What is the lowest x and what's the highest? For this graph, this is the lowest point. What's the x here? What is the x of this point, everyone? Everybody, what is the x of this point?
-5 and -2.
So it goes from -5. That's right. But let's say this is 6. Does the graph stop? Does the graph stop here?
Yes. No, because they have the little narrow that goes straight.
Arrow here. So the x starts from here, from -5. The x, again, the domain is always on this axis. It starts from -5. If this was a circle or a shaded circle, you would stop here, but it does not stop. Even though you see x here, it does not stop. It keeps going up and up and up infinitely. What does that mean? It goes where? Towards what symbol or what number? If we keep going to the right side and number keep increasing as we go to the right, it goes towards what? What do we say?
Positive.
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 6.
Oh, it surpasses 6. It goes beyond 6,
Oh,
beyond the trillion. It goes towards what? What is that symbol or that number?
infinity.
Infinity.
Okay, so whenever you see an arrow on a graph, that means it does not stop, unlike this one. It keeps going and going to infinity. And this direction goes to positive infinity. But the other direction is negative infinity. This one stops here, so we don't have infinity here. We have -5 because the graph stops here. And what are we using again around -5? Is there a bracket or parenthesis?
Parentheses.
Bracket.
Circle, parentheses, and always use parentheses around infinities, both of them.
Okay.
Always use parentheses. Okay, so that's the domain. What about the range of this graph? Give me the range in interval notation. Again, this is what we call interval notation. We only need the lowest and the highest. We don't need all the values because we have too many to list. For example, this one, they do not stop. We have infinitely many. This one we use set notation when we have specific values and we write all of them. Give me the range of this function.
-2
That's right, the lowest one looks like it's -2.
to 4.
And what?
4.
But does it stop here? Does the graph stop here? If the graph stops here like this, then you would say only 4, but it keeps going and going. As you can see, what happens to the y as you go? The y here is 4, here it will be 5. After this, as this goes up, it will be 6, 7. So where does the y go?
So we also put the infinity too?
That's right, so it also goes to infinity.
Okay.
And because the graph on this side does not stop. So both x and y go to infinity, but here the graph starts from here. So both x and y start exactly here. There's nothing below this because of this circle. Unless we saw, like if you had like an arrow here, that means this does not start or stop here, it keeps going. So we would have infinity here too, and infinity. But in this case, it stops here. So parentheses here,
Parentheses and
also parentheses.
parentheses.
Okay, so it shouldn't be hard to get the domain and range from the graph. You just basically just read it directly from that graph. There's nothing else to it. Okay, any questions, everybody?
So Professor, so when we supposed to use the bracket? When the circle is
It's
the
shaded.
shadow?
Yeah.
Okay.
We see it like this, or when you don't see any hole in the graph. This is, for example, a continuous graph, so no problem. But if you see a graph like this, and you see a hole in it, that means this point, whatever it might be, for example, 4 here. So you skip that point. So this point is not included. But if you see a hole, so this is included for included, this is for not included. Everybody else? Anybody? You guys understood all of this? Any issues? Any confusions at this point? Again, this is very important for functions, so make sure you understand all of this. Let me know if you have any questions. So basically, we kind of reviewed a lot of things we've already seen with functions. We reviewed a lot of it. So all this in detail is in the previous 3 or 4 lectures. You can always go back to them and rewatch them in detail. When we spoke about this in detail, spoke about how to decide whether a graph is a function and everything. This is the part that we needed to elaborate a little more on with the domains and range. So it shouldn't be that hard to find the domain and range from a graph. Any other questions before we move on to another thing? No questions. Everybody, let me hear from all of you. Please please let me know if you have any issues, any questions at this point. I suggest you
You're saving this video, right?
well, yeah. I suggest you rewatch it. I know it has a lot of information in it. I know we talked a lot about a lot of things, but again, this is like a review of the past 3 or 4 classes. So make sure we've already seen basically all of this. We've already seen. We just kind of combine everything into one, basically like a little review. Okay, so if you have no questions, let me talk about one more thing. So this was supposed to be 4 here. Now let's do number 5. Another important thing. So domain and range of some different functions, not just polynomial functions. So here's the deal. So we saw linear functions, we saw quadratic functions. We graphed them the other day, okay? So with quadratic functions, they don't stop, okay? The graph keeps, or the parabola keeps extending. Same thing with linear. They keep extending. That's why the domain and range for both of these, even for that one as well, even for the cubic function, you see these arrows here? The graphs do not stop. So all these 3, so the domain is always negative infinity to positive infinity. So whenever you see a question and you have a linear function or a quadratic function or a cubic function, it says, what's the domain? Immediately say it's this. Basically, any number, all the numbers, x does not stop. This means all real numbers between negative infinity and positive infinity because of these arrows. The graph does not stop. It keeps extending in both directions of the x, the positive side and the negative side. Same thing with parabola. If this is the x-axis, as you can see, both x extend to positive infinity and also to negative infinity. Okay, so remember that for those functions. For the range for this, for a linear function, the range is always this as well. Okay, so for linear functions, it's always going to be like this, both the domain and range, because the line is basically an infinite number of points. It keeps extending in both directions infinitely. That's why both the domain and range, they're not limited, they don't stop. It's not like this graph, for example. There's no limit to the x and y. Unlike this one is limited here between -3 or 4, -1 and 2. But when you say arrows, for example, for linear functions, both domain and range are from negative infinity to positive infinity. So you don't have to do any math, you don't have to solve or graph. Whenever you see a linear function, you can write this immediately. For the next function, the quadratic functions, as we saw, the domain is always. Okay, so the domain will always be there also, as you can see, because these arrows, the x extends in both directions. What about the range, for example, is it always something? The range of this graph, for example. Is it always fixed or does it change? The quadratic function is not always like this. It could be up, the graph, the parabola could be shifted up, maybe down, maybe left, maybe right. So the range is not always fixed. It depending on the vertex. This is what we call the vertex. What we call the vertex of the graph. That's the lowest point. Okay. The graph could be facing up or down. This lowest point is called the vertex. So the range goes from the vertex and up or down. You're right here, vertex. Okay, so the vertex is the lowest or the highest point of the graph, because if it's like this, the vertex is this one. But if it's facing up, the vertex is the lowest point. Now, what is the range of this graph? It goes from where to where? It kind of looks like something like, did we do an example of this? No. So what do you think the range of the y goes from? From what value to what value on this graph? What is the vertex, or what is the range? So the x, we said, goes in both directions, but the y starts from where? What is the lowest value of y for this graph?
Comes up from 1.
Nope, starts from here. What is this point over here?
0.
0.
So it goes from here, from 0, and for this specific graph, it goes from 0 to where? Does it stop?
No.
No, it keeps going up to where?
Infinity?
Exactly, so infinity here. Do we use brackets or parentheses here for the 0? Do you see a hole in it? There's no hole, so we're going to use brackets or parentheses around 0.
Parentheses.
Parentheses only if you see a hole in the graph. If you don't see a hole in the graph, it's a continuous graph. So here, there's no problem with that point. Everything's included. The 0 is included too, so we use bracket. Okay, so depending on the parabola, this changes. This 0 changes, but everything else stays the same. This, the domain is always this. The range could be negative here or positive infinity. For cubic function, if you see one, both x and y are like this, because both extend in both directions, no problem. So the domain is always negative infinity to positive infinity, and the range is also negative infinity to positive infinity. So at least remember these three functions. So next time you see them, you can immediately answer them. So remember, for all three, the domain is always negative infinity to positive infinity, all of them. For the first degree and third degree, the range is also that, is also negative infinity to positive infinity. But for quadratic, remember, the domain is always negative infinity to positive infinity, but the range changes depending on the graph. So we have to look at the graph and see what's the highest point or the lowest point, and then see if it goes to infinity or positive infinity. If it's facing up, it goes to infinity. If it faces downwards, it will be a negative here. Okay, so at least remember these three functions. So in addition to these three functions, we will have, there's another section, another part. I don't know if we have time to do that, but yeah, we'll do that another time. So we're going to see next time how to find the domain of, so far, polynomial functions, at least these first three, we covered them. Next time we're going to see some non-polynomial functions. Okay, some non-range of, let's call this, we're going to call this non-polynomial functions. So we're going to see, so this is non-polynomial because it has x in the denominator. We're going to see something like this. When you have, for example, a radical, maybe x plus 2. Actually, let's see. No, we have some time left. Yeah, so we can cover that. So as you can see here, these are not, as we talked earlier, polynomial functions do not have these 3 or 4 situations. X is not in the denominator or the radical. So so far everything we saw is polynomial functions except for this one. So let's see how to find the domain for non-polynomial functions. For example, this one and this one. So remember one thing, whenever you have, there's a number we can't divide by. What number we can't divide by? Does anybody know the number that we cannot divide by? It's undefined or it's forbidden in math to divide by a specific number. What is that number?
Isn't that 0?
That's right. Division by 0 is not possible. So any number division by 0, if you try that in the calculator right now, it will give you an error or something like that. So this is what we call it. It's undefined. Okay. So whenever you have a function like this, and you have some x in the denominator, basically you say the x cannot be 0. Okay, in other words, division. You cannot have 0 in the denominator, in other words. I think I better leave this for another time. It's going to take at least 30 minutes to explain. But briefly, so the denominator of any function cannot be 0. Same thing if you have, let's say 2 and x plus 4, for example. Again, any denominator of any function or any number cannot be 0. For example, here, the bottom cannot be 0. That means x can't be what? If we don't want to have 0 here, x cannot be what number, what value?
Also 0? 0?
No, if you plug 0 here itself, it would be 0 plus 4. 4 will be fine. What value of x should we avoid to not have 0 in the denominator?
Oh, -4?
-4, that's right. So we say the denominator, x plus 4, cannot be 0. And that number cannot be, x cannot
because
be.
it's -4, right? Because -4 plus 4 is 0.
That's right. Or you can solve it, just like you do with equations, you can solve it. And you can find that number that you can't use. So for example here, -4. So for now, just remember, any denominator of any function or fraction cannot be 0. For here, when we have a radical, inside the radical, we can't have a certain type of numbers. What kind of numbers we can't have inside of a radical? Or what kind of signs of numbers we can't have inside of a radical? The radical does not take negative numbers in. Okay, square root like this. You can't have a negative number inside. Again, that's also undefined. For example, -1 is undefined. Okay, remember that inside the radical, square root, you can't have a negative number. You can have a positive number like this, for example, square root of 9 is 3, but the square root of -9 is not -3. It's undefined. We can't find it. It's not a real number, okay? It's not the numbers, the real numbers we talked about. It's not a negative or a positive or a decimal. This is undefined, so remember that. So this has to be 0 or higher. 0 or higher. We say greater than or equal to 0. Okay, anything inside the radical could be 0, not a problem. Radical 0 is 0. Radical 4 is 2. Could be radical 7, which is a decimal, and so on. But it cannot be anything lower than 0. For example, -1 or -2. This is again, we say undefined. So anything under the radical has to be equal to 0 or greater. So we say it has to be greater than or equal to 0. Whatever this might be, take it. Here you say not equal to. Here we don't want the denominator to be 0. Because if you end up with 0 in the denominator, that's a problem. You can't do that. You can't, even if you put that in the calculator, it will give you something undefined. But we try to avoid that point. For example, for this function, we can't use 0. For this function here, we can't use -4. We won't have any value. If you do f of 4 or -4, for this one, if you plug -4 here, it will be 0 here, and this is undefined. we don't know that value. So that's why we avoid using that. And that's actually the reason why this graph looks like this. The graph of 1 over x looks like a hyperbola. As you can see, it does not go through 0. It has two pieces here, but it does not go through 0 because we can't plug 0 here. If you do f of 0, it would be 1 over 0. And this is not possible. Okay, 1 over 0, that's why the graph of this function does not go through 0. These can go through 0, not a problem, but for a function with x in the denominator, there's always one value to avoid, or maybe more values to avoid. At least for this one, it's 0. For this one, the value to avoid is -4, and so on. That's for fractions. But if you have radicals, remember, just take whatever is inside, and you say this has to be greater than or equal to 0, simply because we can't have negatives inside of a radical. Then you can solve this for x, just like you do with equations. You can say -2, -2. So x is greater than or equal to -2. Okay, so these are the two types of functions that are not polynomial. And when we find the domain of these, just look at them and either use not equal to 0 or greater than or equal to 0, depending if you have a radical or a fraction. Let me use a couple examples to clarify this more. So f of x, for example, let's say it's 3x plus 3 over x minus 2. What value of x is not good for this function? What value of x is undefined or can't be used for this function? If you look at the denominator, again, we don't want 0 here. So what value of x to avoid? So we don't have 0 here. Everybody, what value of x is undefined for this function, especially for the denominator?
-2.
It's not -2 itself. If you put it,
+2.
it's +2, that's right, because +2 minus 2 will be 0.
Professor, I'm sorry, interaction. My other class is starting now. Can I leave?
We finish, almost done. We finish at 6, right?
Yes, I have a class also at 6.
Yeah. We're gonna finish that by 6. Just a couple more minutes and we're done, okay? I'm aware.
Oh, okay. All right.
Okay, so just the last couple examples. So again, when you see a function like this, you say the denominator, just say the denominator can be 0. That's it, that's all you have to do. And then solve this to find x. So you say x can be 2. And if you see a radical, what do you do again? If you have, let's say, you have a radical, for example, x minus 5. What do you say about the radical? This has to be what? It has to be greater than or equal?
0.
Okay, so just take this, whatever it is, and say greater than or equal to 0. That's all you have to do. For fraction, say not equal to unsolve. For radical, just say has to be greater than or equal to 0 and then solve, just like you solve fraction. That's all you need to remember from this last part. And this means x has to be greater than or equal to 5. Okay, that's all I wanted to say with these two examples. Fraction, radical. Again, fraction not equal to radical, greater than or equal to, and that's it, then you solve. We'll probably talk about this last part. We're gonna probably talk about it a little more next time. For now, I believe that's it's good enough. Please review all this. I know this was a lot of information today. I felt like we needed to go over this again and review all of it because it's very important and fundamental for functions. So please rewatch this video. And details about each one of these topics, because we talked about a lot of topics today here. We covered each one of these topics in the previous videos and lectures. Please rewatch those as well if you needed more information. Let's see if we can.
Professor, you didn't take attendance.
Yeah, I was about to. Let me see if the portal is working.
Oh, okay.
And okay, again, make sure you rewatch this. I'm sure it will make more sense if it's still confusing now. And if you have any questions, please let me know in our next meeting. But the portal is not working, so I'm just going to take a screenshot of your names, and I'll do the attendance later because the portal is down at the moment. Okay, got it. All right, everyone, that's it for today. Apologies for the long lesson, I know. But again, I'll see you on Monday, yeah. So I'm gonna post the homework.
You took attendance.
I took a picture of it. So before we go, so again, I'm gonna post this lecture. Please rewatch it, and then do the homework. And I'll post the review also to the homework folder soon. Check that out. Finally, I already posted your quiz.
Monday.
Already posted your quiz grades to Blackboard. Please check them out. Also, I believe I attached the corrections.
Professor, when's our midterm?
The midterm is in week 9, the following week, not next week.
So, Professor, I can leave, right?
Yeah,
Yep.
so I'm almost done, just making this announcement. So again, the midterm is not next week, it's the following week.